Okay. Yeah, thank you. Yeah, once again, thank you for inviting me. So though my talk has like quantum computers, it's more like a motivation for the questions that I'm studying. So like starting with like slide 3, there will be nothing quantum computing specific. So don't worry about that part. Right, and so this is kind of very brief motivation why I'm actually interested in this question. Quantum computers is some kind of new technology that the idea behind it is that people want to use laws of quantum mechanics to solve problems that are otherwise very hard to solve on classical computers. And the group I'm working in is particularly interested in solving interesting problems that are not addressable using like modern supercomputers on a small quantum computer. So the building quantum computer is a big challenge, so we haven't built one yet, but we are interested in a question, well, what we can use the very first generations of these machines once we actually can build them. Right, this is what we call a small quantum computer, so something of the first generation. And example of problems that are very well suited for these machines is some problems that are kind of naturally related to quantum mechanics. So something like chemistry simulation or some studies of some structure of materials. And as we're kind of approaching this question from a very kind of practical side, we actually want to understand like all numbers, how actually long will it require us to run certain algorithms, how big this quantum computer should be. And this brings us to a question. So we have some algorithm, can write it down in a very high level way, and then we need to express using the architecture of using basic operations that architecture of a quantum computer supports. And for example, so the basic building block of a quantum computer is called qubit. It's basically two-level quantum system, and in a classical computer, if you have one bit, there is no there's only one operation you can perform on it, just like a bit flip. So it turns out that with quantum computers, even one bit, which is called one qubit, becomes much more rich and interesting, right? And so we basically want to understand how take arbitrary one qubit operation and express it using one qubit operations that our quantum computer supports. And we want to do it as good, as efficient as possible. So, and this is bring us to this formal statement of the problem I'm going to mainly study in this talk. So we are given some set G of, it is finite, and this is a subset of SU2, so 2 by 2 unitary matrices with determinant 1 or -1, right? So then we're given some target element of SU2, and we also know that frequently in almost all cases in our applications, this U cannot be expressed just as a word in terms of U1, Un. So we actually need to approximate it. So we also given required quality of approximation as a part of our input. And the distance function that we're using is just 1/2 of square root of trace v dagger. So dagger is a notation for conjugate transpose of unitaries. So if you have a special unitary like this, uv minus v star u star, where star is complex conjugations and conjugate transposes this. Right, and so our question, we want to find a sequence of elements of set G such that we can achieve our quality approximation epsilon. And we also have some kind of a cost model. So implementing having to implement on a quantum computer each of these elements of set G will come at certain cost. So the total cost of executing approximation to this operation will be just the sum of the costs of each of them, and cost is just some real number. So this is a basic statement of the problem. For this talk, if you have questions about the statement of the problem, I think you should ask now.
Given U1 and UN, or to choose U1 and UN?
No, so given. So this is the input. So you given U1, UN, you given U, and you given quality of approximation epsilon.
Cost function.
Yeah, and also cost function is given.
Is it, so will there be a discrete analog of this also? So suppose I'm in SL2 CP or something, and now we want
So I mean, this later I will explain how this kind of will be related to L to Z for like, for example, QP, SL2 over QP, or but at this moment we're just in a very general statement of the question, and I'm stating it as general because depending on the structure of this set G, there will be different techniques to solve this question, right? So and I'll go briefly through the kind of previous work where it becomes clear. Okay, like more questions about the statement of the problem? So basically, so how in quantum computing, what we have, right? We have some register, which is just basically vector of length 1 in two-dimensional Hilbert space, and we want to execute operations on it. So this means that basically we take this vector and multiply by u, for example. Right, so, and this is what we want ideally to do as a part of our algorithm. We want to like execute u, but we know that we cannot actually cannot do it directly on our architecture. So instead of doing u, instead of multiplying our register by u, we want to multiply it by a sequence of operations that we have, right? So we actually can do, right? And if you like ask, and we still want our output to be correct, so we want to like, when we do this replacement, we want to do certain, do it with certain precision. And then, if you have many of this, we would do each operations with some precision, and we can guarantee that our output will be close to the ideal one. Okay.
You could also have operations on multiple qubits.
Yes. Yeah, so I mean, it turns out that even like single qubit, just two-dimensional systems is already very interesting. So, but definitely, once you actually study this, you at least want to study. Usually, algorithms express like single qubit and two-qubit operations. So, two-qubit operation just like 4x4 unitary, right? So, and ideally, you want to study also questions related to 2x2 case. But I'll comment on this like in the end of the talk. Okay. Any more questions? Okay. Right. Okay. So the first question: when the solution exists, and basically, it's just sort of a restatement of the problem, saying that for any unitary solution that exists, this precisely means that this G generates a dense subgroup of SU2, and dense with respect to this distance. Right, but as I'm motivated by very practical questions, I'm also interested in the question: well, how expensive is actually this solution that exists? And let's just, for now, assume that they all cost the same thing. And from a volume argument, right? So we can show a lower bound that the cost of so there will exist like unitaries such that require to be implemented, cause at least like C log 1 over epsilon, right? And the next question is, well, under what condition this lower bound can be saturated? So, for example, is for any G from here, this is true, right? And here's some brief history of this question. So the first explicit example of G for which this lower bound is saturated was given in Lubotsky-Phillips-Sarnak paper on Hecke operators and distributing points on sphere. There are two of them from 1986 and 1987, right? And so this is, I also have example of this set here. So this is in our community it's called like V basis because kind of V is standing for 5 here. And so I wrote it as.
Is that why it's called theoretic? Yeah, to explain it.
Okay, right. So and so it's written using polymatrices. So X, Y, and Z are polymatrices. So this is just like also it's historical name. For them, they form basis in the space of complex matrices, right? And using them, you can write down this set like this, right? So this was the first example, and later, like people from our community actually tried to construct generalization of this for SUD, and also like in their papers they.
So what is the fourth? So you have X, Y, Z.
Yeah, and identity. This is identity matrix.
The identity doesn't have any name attached to it.
Yes. Well, I mean, sometimes people call all 4 of them sort of.
It has, because your X is identity.
Oh, I'm sorry. That's a typo. I'll correct it in a second. Yes. It's the other way around. Yeah, I'll put zeros here. Okay. Okay, now it's okay. This is okay. So this is so then this paper was trying to generalize this result on SUD, and also kind of as a side effects they show kind of give explanation of why spectral gap implies this log1/epsilon scaling, and they also give some kind of loose bound relating this constant to actually spectral gap. Right, so basically now we kind of see that if you like have Hecke operator corresponding to G, then asking this question is asking if this Hecke operator will have a spectral gap, right? And for this reason, from this result by Bourgain and Gambour 2008 actually resolves this particular question about saturating lower bound for very wide class of sets G, because it says, well, if G is already dense in SU2 and has entries as algebraic numbers, then it has spectral gap, right? So, and it turns out that for our applications, this is always the case. So, and also there's was a letter from 2015 by Peter Sarnak where he was interested in this value of C. So was actually the explicit value of C depending on this G. And to talk a bit more specific about it, I will need kind of explain a little bit more, so I will talk about it later, right? And this is kind of short summary of results on the non-constructive side of the question. So it tells us that if we have spectral gap, then such an sequence will be always exist, such we can achieve this log1/epsilon scaling with the quality of approximation. But the next question is actually, can you find it constructively, right? So can we have an algorithm that allows us to find this sequence? Because if you want to run something on our computer, we should be able to fast those sequences pretty fast, or to find those sequences pretty fast, right? And again, an application. So now I will give a brief review of solutions, right? So one other kind of slightly different take on this question is, if it just assumes that G is dense in SU2, there is an algorithm that allows us find the sequences that will scale like log to 3 plus delta 1/epsilon. The equals will scale. And the good news also that it runs in polylogarithmic tie on 1/epsilon. And quick comment is, so when we talk about runtime, it usually means about in terms of just 1/epsilon, right? So it's so we allow like arbitrary precomputation based on G, and in particular, this algorithm will require you to do such pretty huge precomputation first before you can build this approximation. And kind of the other take on this question is very kind of naive algorithm where you just enumerate all possible sequences of length 1, length 2, or cos 1, cos 2.
So you allow pre-computation, you
Yes.
allow to prepare big tables or something?
Yeah, so for this particular one, you actually prepare a big lookup table. So you
Exponential in log of 1 over epsilon?
no, it does not depend on epsilon, right? So, it just depends on g, right? So you allow to pre-computation given g, right? So somebody gave you g, and you can pre-compute.
So the point is, if you're given some bad guys, you have to first wait till you kind of randomly walk near the identity.
Yeah.
And then once you're there, then it'll be.
Yeah, so you sort of need to like, so the idea there is you build epsilon net up to some epsilon. And once you reach certain threshold, if you're epsilon above thresholds, then you can kind of bootstrap your approximation from that epsilon net, covering like SU2. Right? And also the constants inside big O will actually depend on the kind of quality of epsilon net you was able to build. So this is the features of this algorithm. And so the other side of the question, right? So if you like do a brute force search, so you basically enumerate all sequences up to certain cost and just do a lookup, right? And this is known to scale. Like memory and runtime will just scale like 1 over epsilon to some p, just positive constant. Right, but then combining our previous non-constructive results with this algorithm, we'll know actually that we will saturate lower bound. And the very kind of natural question to ask if you can have like good parts of both of this, right? So if you can have logarithmic scaling of a length with a required approximation quality, but still run in polylog of 1 over epsilon. And the other more kind of practical note that I will show some kind of numbers with a typical regime in which we kind of run these algorithms, and from that numbers it becomes clear that even if you're kind of being very practical, you cannot be okay with brute force search, right? So this kind of a problem that people actually interested to solve in some regime where brute force search is not working anymore.
The first one might be practical, right? Because you only
Yeah.
have the polynomial.
Yeah, and also I will show some numbers illustrating why we're actually concerned about this 3 plus delta versus just log, right? So why it's actually kind of a big, why in practice we actually care a lot about difference between log and log cubed. Right? I will in a couple slides show you real numbers for this, right? And also in previous work, we're given like 4 examples of this set G, for which runtime is polylog 1 over epsilon, and cost of approximation scales like log 1 over epsilon. But runtime is so the statement about the runtime of this algorithm and even like about the termination of this algorithm is subject to certain conjectures, right? And hopefully later I will be able to talk about this in more detail, because our work is also we wasn't able to get rid of these conjectures and still kind of just rely on more general versions of them. Right, so and this is pretty recent results and coming from a quantum computing. So there is first one from 2012, and so when I write Clifford plus T, it's just sort of a name used in our community, and it's this one, right? So this set G contains this x and y rotation by pi over 4, where this, for example, z rotation by angle phi is just exponent of poly z. This phi over 2, right? So this is why people looked at this one. It's one of the Gates says that kind of we have certain architectures of quantum computers, and this corresponds to the most popular one and maybe the most promising one in our field.
They implement these gates?
Oh, yeah. So once I think the first ones that people kind of work towards building, once they will implement these ones. Yeah. So so this is yeah. Let me kind of, if like in the end, I can kind of elaborate a little bit more if you're interested. Okay, so this is a first result. So second result was by Bokharov, Gurovic, Svorov, my colleagues from Microsoft Research, showing the same algorithms for this like V basis, right? For this one, and also I worked on this the other set G that's related to Braiding Fibonacci anions, and Fibonacci anions is kind of another branch of how people might try to build fault tolerance how people might try to build quantum computers using kind of some topological effects. So this is 3 examples, and there is like a couple more papers from 2014 to 2015 on these topics. In particular, there is improvement of work 1, improving constant factor in front of log 1 epsilon, and improvement of also work 2. And extension, including rotations, like instead of pi over 4, they have pi over 6. So this is kind of all results that were known on this topic before kind of this work I'm presenting. Right. Right. So and so what is our result? This is a result kind of coming from 2 papers. And in a couple slides, you'll understand kind of why there is like 2 papers. And so we have algorithm that works for wide class of the set G. It has polylog runtime. This cost scales in log 1 epsilon. And here we have like kind of two kind of comments. So first, it's again like works under certain number of theoretic conjectures. And second, we again need to allow arbitrary precomputation based on G. And this will become clear that it turns out that on this precomputation stage, if you kind of do not allow this, then we'll have to, we wouldn't be able to claim anything about runtime, because indeed on precomputation stage you'll have to solve pretty hard problems, but those problems are just need to be solved once for gates at G.
Just a constant size group, right? The precomputation is just on an input of a constant size.
Well, so in this case, it's very different precomputation. So you just solve certain problem, actually certain number theoretic problems. So it's not like about kind of building database anymore, and it just precomputation just depends on G, right?
So like G is constant.
Yeah.
Of constant size. Okay.
So you know, like there is one precomputation we would need to do like on, if we given, for example, V basis, right? Just solve some problems related to, yeah. Let maybe like go further. You'll see like what are those problems, and will become more clear. And we can ask some kind of a more general questions that is pretty hard. So actually, what is so special about G, such that these algorithms exist, right? And our work is sort of gives some indication of what is actually mathematics related to this, and maybe hopefully one day people will be able to address this question, and it will be important for quantum computing, because then if people design new architectures, they will understand that they actually need to design architecture such that this instruction sets have a good property, so you can actually compile for them efficiently and get. Right, so this is, and here's like some numbers just explaining why brute force is not good, and why Solovay-Kitaev is not good enough. So this is example. So people trying to find some problems that they're going to solve on a small quantum computer, and just understand like cost of solving them like from the top to bottom. So and this is one of examples. So it's like simulating the spectrum. So basically studying the spectrum of ferredoxin, which is related to photosynthesis reaction, is kind of very interesting kind of molecule that people kind of trying to understand. It's important to understand the structure of this molecule to understand questions related to photosynthesis, for example. And you can see that number, so this rotation stands for single qubit operations, right? So number of single qubit operations will be like 10 to the 6, 10 to the 7, and the precision of output is that we want is 10 to minus 5, so we need to distribute this precision over all rotations, and this way we get numbers like each of them must be approximated within 10 to minus 11, 10 to minus 12. And here's a comparison. So how this, what is the difference between Clifford plus T and Solovay-Kitaev? So if you want to get to 10 to minus 10, we'll have our cost will be about 3,000. And if you want to like run something like 10 to minus 10 using this number theoretic approach, then we will get cost around 100. So we get like 30 times difference. And if you think of somebody running some algorithm to solve some real problem, it can be a difference between a day and a month. So it's kind of people here also estimated kind of time per operation, and so this is sort of puts you on a border between being able actually to solve some interesting problem on first quantum computer you can build and not being able to solve this problem. So that's why we're kind of very interested in this question. And there is like and again, like to mention, why brute force is not working, right? So it's a pretty big number. Right? So if you like also work out memory requirements, you actually will see that if you even have some cloud and can distribute this computation in the cloud, you still won't be done to this precision. So we need these methods, and this is more kind of motivation for people working in quantum computing. So, maybe they'll like think in very applied way and say, well, we're gonna just like build this Clifford plus T thing, and we don't really worry about anything else. But well, it turns out that like all these questions, they're not completely settled. They're actually areas of active research. So we might actually design new architectures that might be better, and we might one day have a quantum computers based on that are topological. So and this all will change the set of gates that we can work with. And also, once we actually know the traditional architecture, we can also try to extend this gate set using some other techniques. So we can try to get more gates, just in this ones, for example. Instead of pi over 4s, we can get pi over 8s, and try to like even kind of bring costs down further. Just kind of improving constant factors, and it's very curious why actually this algorithm work in polynomial time. So this is so now I can tell you a little bit about how the solution works. So the solution while solving these problems using number theoretic approach, we break it down in 2 steps. So first, we approximate our target unitary with an exact unitary, and I'll give a formal definition of what it is later. But kind of informally, this is a type of unitary that we can express exactly using our gate set, right? So you just can basically write some kind of finite length word and get a unitary, right? And what is so originally we basically sort of figure out this structure in a very ad hoc way and just solved, going this kind of 2 stages. And later, so this first paper is about basically trying to understand what's the underlying structure under this exact unitaries, and it turns out that it's related to integral quaternions of a number field. Right, and in the second work, we present this algorithm to approximate with integral quaternions, and then, while again in early works in this area there was sort of ad hoc way of going from here to here. So now it turns out that this is actually quaternion, just factoring quaternions, right? So it's so you can also similar to numbers or algebraic integers. you can study factorization of quaternions, and there is a nice factorization series that we're making use of to solve this question. Okay, so now we can go in a little bit more detail, kind of understand this, explain you some kind of basic ideas how this works. So first, so there are like kind of two sides here. First is the data structures. So how we actually represent objects we are working with, and frequently, this is kind of very important when you solve problem, because choice of data structure can make some questions much easier. And then there is like two parts of two algorithms, like approximation and factorization, which I call like factoring on steroids. Okay. So so all this, kind of turns out that non-constructive aspect of this is very well studied, and so like for quantum computing audience, I think like first time it was kind of explicitly brought to our attention was like Peter Sarnak letter from 2015, that it's actually related to like studying different problems regarding like S-arithmetic groups. So like, for example, understanding if given S-arithmetic group is finitely generated or finitely presented, and computing those generators, or solving a word problem. Right, so this is related, and I think so this only recently there was some work actually telling how to solve this problems explicitly, right? And I think this is a little bit backwards, because I really wanted this one. So so in 1985 it was shown that all these problems actually decidable for S-arithmetic groups, but this algorithm turns out it's not very practical. So so indeed you can compute S-arithmetic groups, so you can find generators and relations, but it's not practical. So and there is definitely no implementations of that algorithms. And over the years there were like several examples of solving special cases of this problem and analyzing its complexity. And I think this thesis does a very kind of good job of reviewing recent results on that question, and also it kind of looks at actually pretty generic statements, showing at least kind of practical algorithms, or it's showing some algorithms that they can prove like complexity of, but they're usually exponential time. And this factorization part you can think of actually related to computing S-unit group of certain quaternion algebras, but we'll see later more details about this. So first, like how we actually represent real numbers. So, like representation using floating point in computer is very useful for asking questions like how close we are to some point, but it's not very good for asking questions if our numbers have some kind of belongs to some number field, right? If it's like, for example, a plus square root 2b, where a and b from Q. And if you're actually interested to go from here to this question, you need to make some assumptions and run some non-trivial algorithms to understand if this is true under some assumptions. And instead, what we do, we kind of go in this representation directly, and we use number fields. So if you're not familiar with the concept, so you can think of elements of number fields as polynomials with some kind of extra relation. This is a simple example of q square root 2. So defined by polynomial alpha squared minus 2 equals 0, and all numbers in this number field of the form a plus alpha b, where a, b rationals. And what is good about this representation, you can perform like arithmetic operations, addition, multiplication, in this representation, then come back to your real numbers, right? And to come back to real numbers, you assign to alpha roots of this polynomial, right? And this is degree 2 polynomial, and there are like two ways to assign real numbers to a plus alpha b. And also, this assumption is field homomorphism, so it preserves your addition, multiplication, division, and so this sigma 1, sigma 2 called an embedding of a number field into reals. and if the number field, all embeddings of the number field goes into reals, this is called a totally real number field. And for the rest of the talk, we actually will be working just with totally real number fields. Okay, so now kind of the other part of the question, okay, how are we going to represent our unitaries? So we are going to use Hamilton quaternions. Oh, this is a table on the bridge, where Hamilton, says that, you know, here as he walked by on the 10th of October, 1843, Sir William Hamilton finds these relations for quaternions. Right, this is a table from the bridge. Right, it turns out pretty well-known old mathematics, right? You know,
tried to rewrite all of science.
yeah, and you know, actually there is some pretty, you know, I feel like talk to modern physicists, say like I'm going to use quaternions, they like look at like you as, you know, trying to do something, you know, suspicious, because but well, in our case, you know, there's very well justification why we are going for it. But coming back, what are quaternions? What are the quaternions? So it's degree 4 algebra, division algebra over R, right? So every quaternion defined by 4 real numbers, and so like real field embeds into quaternion algebra and into Hamilton quaternions, and you know, there are these relations like I squared is -1, j squared is -1, and k is equal ij minus ji. So it's non-commutative associative algebra. Right, there is operation, there is an evolution defined in quaternions called a conjugation, and there is also a notion of a length of quaternion, and also like, I mean, kind of informally I can call it length, but it's also like reduced norm of quaternion, which is sum of 4 squares of coordinates. And the nice property of Q is of reduced norm is that it's multiplicative, right? So reduced norm of 2 quaternion is a product of reduced norms, right? And you know, once we have actual quaternions, we can go to unitaries. So how we do it? We just basically first map each of the basis quaternions to corresponding polymetrics, and then normalize it by the length. Right, so this is a definition of the map going from quaternions, from Hamilton quaternions to elements of SU2. So, and why this is a nice data structure for us? Because, for example, conjugating Q corresponds to conjugate transpose of SU2, multiplying Q by scalar. It's actually kind of insensitive to scalar up to a sign. Right, so basically, if alpha was a negative, it will get a minus sign in front, and nothing will happen otherwise. And it also respects multiplication, so unitary corresponding to a product of quaternions will be a product of 2 unitaries. Right, so this is very important for us, because instead of thinking of factoring unitaries, we now can think of factoring for quaternions. And here's very small generalization. So you can actually put like A and B here. So instead of -1, and so it turns out that if both A and B are negative, this will still be isomorphic to Hamilton quaternion. If one of them is positive, it will be isomorphic to just 2 by 2 matrices over reals. Right. So there are like 2 alternatives. And this will be important on next slides when I'm going to talk about different types of quaternion algebras over number fields. Right, so what we do to get quaternions over number fields, we take A and B, AB now from a number field, F is being totally real number field, right? So, and in general, there can be like, there can be D embeddings of F to reals, where D will be a degree of a number field, which is, you know, for the future, it's one of the parameters that defines how hard actually computationally to work with a number field. So from quaternions number field, we can go into quaternions over R by just, you know, replacing coefficients coming from number field using embedding by coefficients over reals. right? So, and basically when we're going to talk about going from here to unitaries, we need also to pick one embedding, and we just pick sigma 1. So this will give us, so we'll be able to go from quaternions of a number field to elements of SU2. So this is kind of our summary of our underlying data structure. And depending actually what happens to this A and B under different embeddings, there is a classification of quaternion algebras, right? And so quaternion algebra called totally definite if this stays negative for all embeddings of a number field into reals, right? And in this talk, I'm going to focus on this question. It turns out that in our first work, which is about this kind of factorization part, we also address partial and definite quaternion algebras. And but for approximation, it turns out that the first kind of easier step is to do totally definite, and we're currently working on an indefinite case. Okay, so we are doing total definite quaternion algebras. Okay, so now, so if I was talking about factoring, there is one kind of extra thing needs to be told about. If you talk about factorization, you need a notion of integrality, right? And everybody is familiar for rational numbers what are integers, right? So for number fields, there is also a notion of a ring of integers. This is simple example. That if you have q square root 2, that's an example I showed you before, then ring of integers will be just a plus alpha b, right, where a, b now integers. And please, if you're not familiar, don't be confused. It doesn't happens all the time that you can kind of just replace things with integers, and it will be like a ring of integers of a number field. It's a little bit more complicated than that. So now for quaternions, how we can define a notion of integrality? We can define it in a similar way how one would define actually a notion of integrality for number fields by saying intersecting. If we say take elements from here that are roots of polynomials, monic polynomials with integer coefficients, this all such elements form a ring. It's a ring of integers of a number field. So for quaternions, we can also ask, okay, what are the quaternions that are roots of characteristic polynomial with integer coefficients, right? With first coefficient 1. So it turns out this will be degree 2 polynomial, and this reduced trace and reduced norm of quaternion precisely the coefficients of that polynomial. And first coefficient is 1. So when both of them are in the ring of integers, then we call a quaternion integral, right? And the problem here is that we lose one very important property, that our integrality is preserved under multiplication. So because our algebra is non-commutative, right? So actually we take two integral quaternion, we don't get an integral quaternion as a product in all cases, right? So, and how we solve it, we just sort of enforce this, right? So we take subset of integral quaternions that is closed under addition and multiplication, has some extra properties, right? It's a full rank, so if you can multiply by scalars, you can actually get your full algebra. And this is an example, right, for q square for this quaternion algebra, right? This is an example of a maximal order. So we also want to feel, if we would just kind of take a ring of quaternions that are integral, right? And it has a full rank, it will be just an order. But we also want this property of maximality to build a nice factorization theory. So this is maximality by inclusion, right? So this is an order. Order is maximal, it doesn't properly contained in any other order. And this is an example of such a maximal order. Another example, more simple, if you're familiar with, if you look at quaternions, just -1 over q, right? So for that will be Hurwitz order. Will be an example of a maximal order, which is defined as z plus iz plus jz plus 1 plus I plus j plus k over 2 times z. Right, so this is another example of a maximal order. Okay, so now I have a notion of integrality. And basically, when I talk about approximating things with integral quaternions, I actually mean approximating things with the quaternions coming from a certain maximal order. Okay, so this is a now a short summary of the objects that I actually need to specify my exact unitaries. So I have a quaternion algebra of a number field that is totally definite. Then I have an embedding of my number field into reals. Then I have a maximal order. And also I fix a prime ideal of the ring of integers of number field f. And I'm considering all unitaries coming from the quaternions such that the reduced norm generates the power of this ideal. Right? If you're not very familiar with notion of ideals, here's kind of more simple kind of simplifications that if you look at this -1 over q, then 5 times z is a prime ideal. Okay, yeah. I also need to pay attention this is actually prime ideal. Right? And then you can think of this set as all quaternions from a maximal order of the length 5 to the n. Right? And we can generalize this notion by considering prime ideals instead of just primes, right? And also in our paper we actually consider further generalization. We allow lengths to be just powers of prime ideals from some finite set, right? So instead of just one, we can have any finite number. Yes, yeah, and this is precise direct. So this group is S-arithmetic. Okay, so we have exact unitaries, right? So, and here's a sort of kind of appears some disconnectness, right? That our original gate set was just defined using a bunch of unitaries, but now we define this set coming from prime ideals in maximal order, and it turns out that currently we don't have very good algorithmic solution to this question. How you go from here? Is there algorithm that going from here decides if there is such description or if there is no such description, and along that line? So we don't have that, but we have certain guiding principles. How you choose all of this, and we list.
So starting with the S-arithmetic group,
Yeah.
and then you will try to find generators, and then you'll make your gate.
Yeah, I'll go in. It's in the next slide. So
And the vertical, you guys start
Yeah.
with the gates, and then
yeah. So originally what happens that we just took this thing, right, and then figure out that it has some nice properties. Didn't know at that point what is arithmetic and arithmetic at all, and sort of did everything in a very ad hoc way. And but then so. Yes, so the key idea here is that we actually want to start from something as arithmetic, because then we get a nice structure to solve a problem, right? Because if we just start with G, it would be kind of we won't have the structure that helps us, right? So and the question is, suppose we followed some understanding, some guiding principles how we can pick M and P using G, and for an example, right? So we can see that these things Rx pi over 4 can be defined over a certain number field, right? So, well, why don't we pick a real subfield of that number field here, and we can make those principles a little bit more precise. So in application, it's not, for many examples, it's not very hard actually to figure this object, kind of a candidate for this, right? But then we need to go and check, right, equality, and so this is the next slide. So once you're given the set SUMP, so we present an algorithm that allows you to compute the generators of it, right? So we compute a new set of generators, which we call G star, and it turns out that the interesting feature of this set of generators that we compute, it actually allows you to do factorization very easy. So what?
You produce generators and relations.
We don't compute relations. I think.
These are free groups because they act.
No, it depends what the rank is.
Yeah, so it's.
If he fixes one place, because there's arithmetic in one place.
Yeah, so there actually there can be if we can have like let's.
Now maybe finish your lecture. We're going to be talking to them.
Yeah. Well, I'll come back to I mean, it's definitely a very, very good question. So, but kind of what the feature of this set G star, right? So then once actually given element from here, and when I say that I'm given element from here, actually means that I'm given quaternion corresponding to it, right? So then we basically need to take this quaternion and factor it using this gate set just by trial division. And what I mean, so basically you take your quaternion Q, you look at this reduced norm, and you do trial division and see if you make it smaller, right? If you make exponent here smaller. So in this way you sort of can, by trial division using this G star, you can like get your circuit back, right? And in a slide I'll actually explain you what is a kind of mathematical object related to why it's possible. Right, so, and then, one kind of simple solution, once we have this G star, we can just take and express all elements of G star using our original set G, and if we can do it, we kind of get the equality. And, if you were to compute relations, we can actually do it even nicer, right? But
Sorry, what is G star?
it's a new gate set, so it's a new generating set. So this group, SUMP, is finitely generated.
Yeah.
And this is the new set that generates. We have an algorithm that computes G star set of generators of SU2 MP. Given M and P, right?
Arithmetic group, you give a generator?
Yes, for this special case, yeah. And this is something that is kind of, in this generality, this wasn't studied before. This algorithm didn't exist, right? So I think it's kind of one of the main.
Clarify what Grunewald and Siegel did was proof that it's decidable, but you actually making it feasible.
Yeah, we actually have a working implementation of it, and we also can have certain idea of its runtime and relate to other results, recent results, and related to algorithm for quaternion algebra to understand the complexity of actually how hard to find those generators. Okay, so this is how we kind of go about equality testing, right? And this is sort of an idea what actually happens. So we can build a tree where our vertices of a tree are maximal orders of quaternion algebra, and so in turns out this is directly related to Bruhat-Titz tree, right? So it's kind of another small. So if you can think of Bruhat-Titz tree as a kind of in a local picture, so this is a global way of thinking about it, right? So we start with our original maximal order, and when we conjugate by quaternions, we actually move between different maximal orders. So this is another feature of non-commutative case where, in number fields, we have a unique maximal order, a unique reunion of integers. Here, there's infinitely many of them, right? And each conjugation will kind of move you between different ones, and you can actually kind of understand under which condition conjugation will move you or will cause you to stay in the same place. And so in very simple case, the kind of your neighbors of the region is corresponds to being able to move by applying just conjugating by quaternion on all the prime lengths, right? So and again, I also can give you example for a V basis or for this LPS example, right? So in that case, you will have quaternions of length 5 to the n. So the regularity of the tree will be 6, norm plus 1, right? So and each of the Cs will precisely correspond each of so quaternions corresponding to this will be just 1 plus minus 2i, no, 1 plus minus 2, 1 plus minus 2j, right, and 1 plus minus 2k. So it's like integral quaternions, and there will be like 6 neighbors of original Hurwitz order, right, corresponding, and then your tree will be 6 regular, right? And so and this is how you, in this simple case, we define neighborhood relationship. So, and what I mean by simple case and not simple case, so it turns out that this gives you equivalence relation for maximal orders. You take that, you say the two maximal orders are conjugate. If there exist quaternions that can kind of transform one into each other, right? And then you can ask, okay, amongst all that infinite set of maximal orders, how many equivalence classes with respect to this relation? And it turns out there's finitely many. And this is what is called the number of conjugacy classes of quaternion algebra. And when I say simple cases, means that number of conjugacy classes is just 1, right? And this is when you can actually move between these vertices using just one quaternion, right? And so you can think of factorization as sort of a pathfinding in this tree. So yeah, I already mentioned this is tree is norm p plus 1 regular. Okay, so this is how you do it, right? So, okay, 1 second. So you basically try all neighbors. This is an example for P is, for example, prime ideal with norm 2, right? So you have 3 neighbors. You check, compute the distance by just computing the length of quaternions, and checking that your result still stays in the maximal order, right? So basically, kind of do trial division, and then you navigate, you see that you need to move here, you produce first element of your factorization, and then you move to the origin, right? Oh yes, that's good. I think I should, till I started to get embarrassing measurements, I'll turn off my Wi-Fi. Okay, so this is right, but it can happen that you're not in this simple situation, and it turns out it's like happens very fast in kind of things we're interested in our applications. So you can get your class set being non-trivial. So this is coloring of the tree. There are 2 equivalence classes. So yellow vertices are 1 equivalence class, and this corresponds to your original maximal order. And there is one more, which is this.
Fact that for the class number being 1 is very rare.
Yes.
Then you usually it's
well,
in a definite case.
Yeah, in a definite case.
Yeah.
In an indefinite case, it's actually not that rare. But so in definite case, it's you actually there is even like some papers classifying class number 1 quaternion algebras over Q, and I think over quadratic fields too. So there's like not that many, and people classified all of them, right? So and in this case, I mean, the idea is the same, right? So you do a pathfinding, but you actually, so we don't really want to like go and deal with representing different maximal orders. So we do very kind of more simple thing. We actually try to find all generators, right? That can kind of move us around this tree, and then we again do trial division. But in this situation, we don't take like 1 step over the tree, but we can like take, for example, 2 steps, right? So like if you like be here, one of generators will just take us immediately to origin, and if like there was like yellow thing here, there could be a generator that will require us like to take 3 steps. And how we go about building this? We actually can start from this origin and kind of build a spanning tree. So this tree will be infinite, right? But we will build a spanning tree till we kind of can have like yellow border all over, right? And because once we reach yellow points, we kind of found one of the generators, right? We just cannot stop at red ones, right? So for example, here is like will be like 3 generators corresponding to length 2, right? Or exponent of the length equal to 2. Okay, so this is this is kind of a very brief idea how this factorization works and how finding the generators works. So now I'll move to how we solve approximation problem, and here we actually restrict ourselves to some subset of target unitaries, which is this Z rotations, and so first motivation for this would be actually practical, because this is what most frequently happens in kind of problems we need to deal with. But second, it turns out that in this case we know how to solve a problem with I mean chemistry, all this chemistry stuff.
Only require diagonal?
Yeah.
That's it?
Yes.
Hardly a useful.
Well, I mean, there's, I mean, all the kind of complexity is in multi-qubit part, right?
Yeah,
so, but
I understand, I mean, if you are clearly the multi-bit thing, better you do this.
Yeah.
The rest is built
Yeah.
from.
And I'll actually, well, so this is, I think this is kind of, it turns out that, when people think of all these problems, they actually have, just in the quantum computing community, they have a certain way of thinking about them. And this is just mainly a result of the way how they think, right? So this, it's not like result of, some good reason, for like good mathematical reason. It's just like how they sort of solve their problems, and they just end up having those guys. And if you don't care about your constant in front of a log of 1 or epsilon, you can decompose any unitary into three like Rx, Rz, Rx, for example, right? So it becomes relevant as you actually be very good in terms of the constant that you get in front of log 1 or epsilon. And now I can actually talk a little bit better about these constants, right? And
Those constants are exponents. That you can put any effort you want into them. They're really exponents. Any constant in front of a log is secretly an exponent.
Yeah. So those are exponents, right? So it's,
This is not monkeying around with silly constants. Exponents are what the subject is.
yeah.
In what sense are exponent? Just if you look at all the possibilities, or what? I mean,
Okay,
this is the length of the problem.
Right, but the
Yeah.
number of words that you're creating in every image is so if you look at it number theoretically, it's an exponent, and this is dramatic improvement if you make an exponent on chart, as opposed to 3 times what it should be.
Okay, so this is a sub-problem. So this is a other problems that we're solving in the second paper, right? So we given this kind of description of this exact unitaries over total definite quaternion algebras. So we again work with the same distance, and we given quality of approximation epsilon, and this is our target unitary just specified by one real number. And we want to find basically quaternion from M, such that this is distance is small, right, and that its length is kind of bounded by so L will be target length of quaternion. And as we saw from previous, so this L basically defines the length of the word we need, right? In a simple case, it's precisely the length of the word. In more complicated case, it's function. Basically, the length is a function of it, right? And basically, kind of the whole understanding, right? So the whole question how we want to understand what the relation between this epsilon and L, right? So how so you can think of, so this tree has once you kind of go further down the tree, So kind of going increasing. So L is just a depth of the tree, kind of layer of the tree, and we want to like understand how well we can approximate with a part of the tree up to certain depth, right? And so it turns out that kind of like so. In that letter by Peter Sarnak by 2015, he actually looks at can you prove at what can you prove about this constant, right? So, and this is relation precisely tells you, right, that the length so the length of the depth in this tree must be less or equal than 4 log 1 epsilon plus c. So and you can ask, what this actual constant should be, right? And there are several results in these letters that basically discussing that actually worst case lower bound is 4, and at least for some kind of special cases, and I think this kind of argument probably works for more general situation. And and under some condition you can prove that this will be like 3. Some kind of other notions, some more. I think I won't go like right now into the details, right? And so we kind of aim our algorithm to satisfy this worst case situation, right? So which corresponds to this 4. And basically, what is our result is about that as soon as you make this for some additive constant c, where this additive constant just depends on this, right? So as soon as you can make it. Your length satisfies this inequality, you can actually find the quaternion of this length and then find the circuit. So this is our kind of main result of the second paper. Okay, and just very briefly, how we go about this is kind of the things that the situations that we work with diagonal matrices allows us very nicely separate this question in 2 parts. So on the first step, we actually satisfy the inequality. And on the second step, we satisfy the conditions that our length of quaternion should have exponent L here. And on a high level, so first, what you do here, so this is an example how this would look if you like your f is actually q, right? So then it turns out that this distance will actually depend only on these first 2 coordinates of a quaternion. And
just to emphasize, this way is using its diagonal.
Yeah, this way.
He's approximating a diagonal guy, so the second 2 ones are going to be.
So this expression, because this is diagonal, this expression does not depend on this. It just depends only on 2 of this. So this way we can sort of first pick 2 of this, and then find 2 of this, right? And how we pick them, we actually solve this inequality and look what is the requirements, right? So where this points should be, and for a second we can think that A1 and A2 being just like algebraic integer, or being like, so this together embeds into degree 2 extension of the base field. Which is also, when we work with total definite quaternion algebra, is CM number field, right? So, and now this is, in case of Q, this will be degree 2 extension of Q. So this precisely corresponds to a lattice in a kind of in a plane, right? And what we need to find, so epsilon gives us kind of this level here. So this roughly this thing depends on epsilon, the width, and position in the circle like this depends on phi. So it gives us certain region. And for this condition to satisfy our points, we just need to take a lattice points within this region. Right? So we want to sample those points. And then once we want to solve this part, we actually again solve the relative norm equation between this number field and this one. Right, so kind of 2 parts. And so I won't go like in the details of how this works. Yeah. Okay. I'm wrapping up. Sorry for more. So basically, let me quickly kind of tell you, just highlight the problems you need to solve here. So actually, how we go about the sampling, we actually reduce it to solving approximate closest vector problem in a lattice. And once we actually have like not over Q but over some degree D number field, which just will be 2D dimensional lattice that we are solving approximate closest vector. And you know that depending on this approximation factor, closest vector problem can be very hard. But it turns out that approximation factor influences only our additive constant, so it doesn't change that. Let me show. So it doesn't influence this. It just kind of goes into here. So we can actually, use techniques that work in polynomial time for that. Then there is another instance of closest vector problem we need to solve, and I think I'll skip this. Please ask me questions later. And then the second part is norm equation. So it's also interesting that complexity of solving norm equation is kind of question that is not completely answered. And in our case, to get polynomial time algorithms, we actually need to reduce our attention to special subset of norm equations such that the right-hand side is prime, and then we can solve it in polynomial time. Or in particular, we can reduce it to this is what I call easy instance with prime right-hand side, to a constant size, to a norm equation just with a constant right-hand side using LLL.
I mean, if it's quadratic, this is even deterministic by scope and ELA.
Yeah.
Yeah, these are even deterministic. You can compute.
I mean, like quadratic extension of.
A squared plus b squared.
Oh yes, yes, yes. Yeah, if you like quadratic over Q, there is like.
But even after number fields, you can use an elliptic anyway.
Yeah, I mean, we try to kind of do a survey of like all methods, but maybe we miss something.
I mean, the triple L is usually in D. You're not making D large, right?
Yeah.
D's fixed.
Yeah.
Dimension's not getting big.
Yeah, our lattice discriminant is getting big, but okay. So this is kind of just very brief mention of ideas related, because I don't have I won't go into more details, and let me just conclude right now. So basically, what we have to summarize what our work is about is. We found this class of set G, right, for which we can actually approximate things in polynomial time, right? And also our constant factors actually turns out to be worst case optimal. And let me quickly mention that I didn't mention the conjecture. It's important, right? So the conjecture, there are two kind of questions here. First, right. Once you want to solve this relative norm equation, is there like, once you sample these points, there are some points for which this norm equation is not solvable at all. And then, so first you need actually to guarantee that this algorithm terminates at all, you need to know that there will be like at least some points in here for which there exists a solution of a norm equation. Right, and this is related to studying the value of this exponent. So if you can prove results about that exponent, you can guarantee that there will be enough points for which norm equation is solvable. Second question is, so this how many easy instances, right? So it's even stronger than that. You actually want to like know how many right-hand sides will be prime, or for example, big prime and small factors are bounded, right? So that's not a big deal if you like allow some, right? So and that's the kind of the second conjecture, right? So we basically, to summarize the conjecture under which we're working, we're basically saying that there are like enough points such that there is enough instances of this simple norm equations. Yeah. Right, and basically, to reduce to this conjecture, it just proves that we can sample almost uniformly from this region. So this is what we prove, right? We prove that we have a procedure that gives you uniform samples, and kind of almost uniform again up to some constant. Okay, so this is and to conclude, so again, so we found this algorithm that works in polynomial time, and on the pre-computation stage, you're allowed to solve, for example, compute the unit lattice of a number field, which is known to be a hard problem. Like under generalized Riemann hypothesis, it's an P intersect co-NP, and so. But if you like parameters of a number field are small, then you can solve all these problems in advance, and just kind of have a polynomial time algorithm to compile. And so kind of two open questions. So one kind of immediate open question is how we do the same thing for indefinite quaternion algebras. Then another question is, okay, can you go like to SUD, right? Because the result about the spectral gap is also known for SUD, right? And there's one paper from our community that gives example for SU3, so you can actually have this, but constant factor in front of log is kind of very loose there. But at least there is one example that's actually possible, right? And basically, here's like kind of more general question: what is a good algorithm for actually computing in as arithmetic groups? So that's kind of still turns out to be like just done for some examples, and there's like kind of a lot of work in that direction. This needs to be done. Okay, yeah, thank you for your attention. Yes.